Welcome to my talk on the importance of the build system target model. All right, first a little quick introduction for those of you that don't know me. I'm one of 5 founders of a company called Kitware. We do open source scientific computing software. I'm currently the CTO. I have a very short, boring list of jobs that I've worked at my whole career. I worked at GE Corporate Research and Development from 1990 to 1999 in a computer vision group. And I'll get into some of the stuff I did there actually in this talk. And then from 1999 to the present, I've been at Kitware. What I'm known for, the CMake guy, Kitware guy, and the crazy sandal guy that runs 100 miles in sandals. Give you a little insight into what it takes to create something like CMake. You really need, that sort of persistence. The ability to run all through the day, all through the night, I'm still here. All right, so we're going to be talking about target model, so I thought it would be interesting to define it. And I asked ChatGPT, and I thought it actually did a pretty good job. In modern CMake, the term target model refers to a paradigm shift introduced in CMake in recent versions. I'm not sure it got the reversions quite right, but the model emphasizes organizing projects around targets rather than directories or files, where a target can be an executable, a library, or some other kind of output in your project. So I think this is sort of key to it, is organizing your projects around targets rather than directories. And a lot of what I'm going to be saying today is in this paper. How many people have read this paper? 1.2, maybe. All right, good. So I won't be, that's good. Only Brett will be really bored when I go through a lot of this stuff. And I want to thank Ben Bazel. He works at Kitware. He's on the ISO C++ tooling group. He wrote this paper and came up with a lot of these concepts. But the basic idea here is that dependency flag soup needs some fiber, and I'll get into what that means. So really, what are we trying to do with targets? Stepping back, a few steps, we're trying to organize large amounts of code, and we're trying to reuse that code. Sort of the name of the game here. So, in the beginning, there were simple programs, and you could put them all in one file, and you could just run the C++ compiler on that file and execute it, and it would do what you wanted it to do. But, putting all your code in one file, that's not going to scale, and obviously, coders love to write code. We're going to write lots of code, and that's going to grow, so, maybe put it in 2 files. You can compile that. But, eventually, hey, and this is kind of the evolution of me, like learning how to program. I'm going to stick in these things called libraries or archives or shared libraries. And then you're getting a little more complicated with the build. You got to build this either an archive or a shared library. And then down here on the bottom line, I'm compiling this main.cxx with this minus little l flag that says, link to great stuff. That all looks good. But wait, there's more. What about the include flags from great stuff? All right, so I have to add a minus I flag to build my main.cxx. What about minus D flags, compiler flags, et cetera, et cetera? There's a lot of stuff that goes into consuming a library. The location of just the .a, .lib, or .so is not enough to consume a library. And software is getting huge. So this is from a talk from the SPAC package manager, which is a package manager for building on HPC systems. And this is just amazing stuff with some of these modeling systems that have 98 packages, 248 dependency edges. These are giant, massive pieces of software. So it's really all about that organization. And I would argue that it's about communication. And today, a lot of the communication sort of looks like this. Got some strings, some cups, and then lines of communication between the people writing libraries and the people consuming them are weak at best. When what we really want is sort of the backbone of like the Aurora supercomputer. Seen in the background there, you can see all the cool fiber optic stuff that's connecting these computers. We want a much better system. And that even showed up in today's keynote. I snapped a picture, and we can see communication came up there, right? So carrier pigeons, flags, a lot of that is what's going on today, or has been going on with C++ ecosystem. So communication from library maintainers to consumers. So who are library consumers? Well, there are other targets in the same build, so inside your project. There are other builds using the same build tool, so CMake to CMake. So I build my library with CMake, I have it export some stuff, and then you use your project using CMake, and then you can use my project. Or they might be other build tools using library. Say I build something with auto tools and I want to consume it with CMake. Or they might be package management systems or IDEs. This line of communication needs to be there in between all of these tools so we can have nice things. So this is a shot from Qt 6's documentation on how to do a hello world. And they're using CMake, and they've got target link libraries, hello world private into Qt6 core. And then they note in their documentation that this will not only add the right arguments to the linker, but it also makes sure that the right include directories, compiler definitions are passed to the C++ compiler. So what are library usage requirements? Basically, described in the build, I want to say, add some library foo, and then I want to link to that library bar. And I want to be able to use that in the project build tree, and I want to use it from the install tree. So a little bit of history. How did we get here? What's sort of other attempts at this communication that have happened over the years? Well, like I said, it's all about organization of code. So, as code grew bigger, you started with one directory that had all your code, but eventually developers were like, hey, this file system thing, we can store our code in there. So we'll store related code together in subdirectories. And we'll say, each library executable gets its own directory. So this is just a quick drop into VTK, and you can see the different subdirectories and the files in there. So that's a common way of organizing your code. Makes sense. So the people that wrote makefiles were like, great, that's what we'll do. We'll have recursive makefiles. This was grabbed this off of some documentation on how to use make. And then you can see here that they're setting CPP flags to be -i user foobar. That tells it to search for header files. And then inside there, they use this $CPP flags. And now oftentimes when you see make systems, that's what they'll do. Up at the top, they'll set some flags, and then they'll cascade down into those subdirectories. Seemed like a logical step for people to take, and things seem to work. Now this is sort of a blast from the past. So when I was at GE, I worked in this computer vision group, like I said, and I built this system called Target Junior. It was basically a system for doing computer vision work and multi-view geometry. And we had a GNU make-based build system. And you'd say, library was multi-view, and the rules were that each directory could only have one target in it. And then I found this particularly funny, so I thought I would share it with you folks. You can see that it builds a multiview.a for static Unix builds, and then a scream multiview.dll for the gates of Hades. I'm like, what is that? I didn't even remember this. But actually, you could click on it.
Horror and moral terror are your friends.
So I think they were making fun of Windows DLLs and the whole window system. So programmers are always having a sense of humor. And this is like, the whole Target Junior thing's not even around anymore, but this webpage about the makefiles is for some reason, with that link. All right, so like I said, code bases are getting larger and larger. So just thought I would take a look around LLVM, throw a git grep in there. This is probably not a completely accurate way to do it, but 200 plus libraries, 57 executables. Obviously, you couldn't just find star.cxx, pipe it into the compiler, and produce Clang. Right? There's a lot more that goes on into that, and a lot of interaction and a lot of special compiler flags involved in composing such a complex system. So how have people solved these problems over the years? Well, there's package managers. Some common package managers: Anaconda, VC Package, Conan, Spack, Homebrew, Nix, Ports. I'm not going to go into which one's better or whether they're good or bad. They're definitely things we need. There's platform package managers. And what are these package managers doing? Well, they know that Project X requires Project Y. They know how to build Y acceptably for Project X. And then they can tell X where Y is, especially in the case where there might be multiple installations of Y. So that's kind of the job that package managers do. But there's a problem with this that I see, is that package managers are great, but there's a lot of duplication going on, right? Because each one of the package managers has some sort of spec library that the group maintaining that package manager gets together and figures out basically all this stuff for every project they can build. Like, okay, X requires Y, here's how you build Y, and here's the special flags we need to do that, and here's how I can inject it. So for each package manager, and then for each package in them, there's a whole bunch of recipes for each of them. So wouldn't it be better if the specs for foo were instead communicated from the original author out to the different package systems? Do I have hands? Do we agree that this would be a better world? Yes, consensus. I'm not exactly sure how we're going to get there, but we definitely want to get there. All right, so other ways this has been solved sort of in the past. Simple flags from a single installation prefix. So I've got my main net here, and I include this foo, do cpp main.cxx minus l foo. And this is just assuming that foo's been installed in user include and the library's in user lib and everything's implicit. And a lot of Unix development happened like this for years. And it was okay as long as you're using system libraries. But as developers started adding more libraries and building up their ecosystems, this kind of breaks down. And it doesn't work unless everything's installed into the system, and then there's all kinds of troubles with that. Auto-linking, this is a thing that you see a lot on Windows and some of the libraries I've seen that can definitely confound developers. I remember running into this early on in my career and like, why is it trying to link that? Like, where is that coming from? It's not even on the command line. But someone put a pragma comment lib foo inside of the source code, and this told the compiler, all right, well, hey, when I get to linking, I'm going to link this foo thing in there. So the problem is, where is foo? Right? If I get around to link time, foo might not even be around. What about the other flags that I've been talking about? You're seeing a running theme here, that you need these flags in order to use something. All right, so other people have solved this by compiler wrappers. Does anyone here use the MPI library? You got one? Oh, you got two? Okay. It's a message passing interface. It's for creating parallel programs. And their solution to this problem was to write compiler wrappers. So instead of calling G++, you would call MPI++. And then it would inject a whole bunch of weird flags that you didn't know what were during the whole compilation thing, and then build your program so that it could work. Fantastic, right? It works great. But it's not composable, right? What if I want to use MPI in CUDA, which has MVCC? You've only got one driver here, right? There can be only one of these. So it's just not scalable to have compiler wrappers. But yet they still exist. So again, ways of communication, sort of getting back to this flag soup concept. You could have some sort of program that spits out a bunch of flags and execute that, run it, and give it to the compiler. But then you might ask yourself, what are those flags? What do they mean? What's the context of those flags? And oftentimes these tools would spit out flags that are GNU-based, right? So they work with the GNU compiler. But there's a few examples here, -pthread for GNU versus -x compiler pthread for CUDA, pick versus qpick, different ways to specify OpenMP. There's no real standard way in these tools to specify I'm using vendor X's compiler. And then some tools took it into their own hand because they really wanted that communication, right? They wanted that fiber. They wanted to talk to the people using their software, and they wanted to make sure that it could be used correctly. So they said, I know what we'll do. I'll write a tool that I ship along with my project. Here's an example where FreeType, now they use pkg-config, but they originally had a solution called FreeType-config. It was deprecated because it couldn't reliably use with cross-compiling. It's another issue that comes up with this. But they really wanted that communication, so they use pkg-config now. Another tool that did this, libpng, had their own config. And you can see it spits out things like the library prefix, install dir. So this is all the information about that you need, right? This is how to consume this library. The library took it upon itself to create a tool to do that communication. And then the very popular, PC files, pkg-config, they're widely used to provide flags. Very popular on Unix-like platforms. Windows, not so common. A few people try to use it, but it's so infrequent that you can't actually depend on it and count on it. So it really isn't something you can use if you're doing something cross-platform. Another issue that I tend to see with pkg-config is that it tends to use -L and -l pairs, where -L tells you what directory something's in, and -l tells you what to link. But this can create ambiguities if the library exists in more than one L path. So this is a contrived example, but let's say I do this C++ -L user foo, L foo, right? So then I'm getting my foo, and then -L user bar, L bar. So it all looks good, except when I look in my directories, I can see that there's a libfoo.a and a libbar.a in the user foo path. So now, what's the compiler going to do? It's going to grab that first libbar and get the wrong one. And then who knows what's going to happen, because I've linked against the wrong library, not the one that I was trying to use.
You don't know if libfoo is using libbar from /usi/foo, so it might be that even the second one is wrong too.
Correct, yeah, you don't even know which one. Either of these could be wrong.
Yeah.
Or they could all be wrong.
Exactly. It's simply that foo and bar doesn't mix.
Exactly. So there ought to be a better way. All right, so build tools have stood up to the challenge. All right, let's take a look at auto tools in zlib. All right, so I write an AC check header, look for zlib.h. That's going to search around on the disk and see if it can find a zlib.h. And then I'll check for the libraries, and I'm going to look for some library called z that's got a function called gzopen. And I'm going to output a error message if I don't find it. Looks reasonable. All right, I've got some issues with this. The zlib.h that found might not go with the libz you found. Then you're going to be in trouble. What should happen, I think, is you should find libz, which should include the zlib.h, or a specification that packages all of that together. Looking into CMake, we made this same mistake early on because we wanted to be useful, right? We wanted to create that tooling, the useful tooling that was in the keynote, right? We knew developers wanted to use all these packages, and our instinct was, great, let's add a new find thing for every time someone wanted to use things. So people contributed these into CMake. And I think there's like 179 of them in there now. So there's a whole bunch of things in there that CMake knows how to find. But what's wrong with that, right? What lessons do we learn from that? So the original ones looked for an include and a library. They found some .h files, some library files, stuffed them into some variables, and it was exactly like what I showed you in the auto tools world going on. Basically this flag soup. Maybe a little better. It found the files, linked them, but it still didn't link everything together. Headers might not go with libraries. Libraries might be in multiple locations. CMake used to have it still had something that could actually scan through your -L paths, and it would report if it saw one of the libraries duplicated, like, hey, warning. That's what the world we were dealing with was, right? Because people did that, and we added a warning in there because it was such a common error that we thought it was important enough to actually encode it in CMake to search your L paths and see if you can find two libraries. And obviously, there's no right answer as to which one to pick. You can just warn and say, hey, there's two of these lying around. You should probably fix this and hope they catch it. But the real answer here is that find* shouldn't ship with CMake. It should ship with the thing being found. And it should be provided not in CMake, because you're always going to run into a version problem here. So if a new version of, let's take one of these. If a new version of OpenACC comes out, it should be able to communicate to CMake that things have changed. Maybe it added another library that I need to look for that CMake needs to know about. Maybe it added different include files. Maybe whole bunch of different things could happen. So it really shouldn't be in CMake code as to how to do that, because the library creator knows what to do it. So hence came usage requirements. Before usage requirements, CMake worked a lot like those recursive makefiles, and it actually traversed recursive makefiles. And then you had global commands like include directories, compile definitions, compile options, and you would put these in your CMake code, and it would flow down the add subdirectories. But that doesn't really answer that consumers have to know. Eventually, they want to know the dependency generated by the build files. Does this dependency use any new external package? So CMake really had an evolution from sort of this flag soup to the ability to import and export targets. The original CMake didn't even have transitive linking. So you used to just have to, you'd stuff all your libraries in a variable, and then you usually like repeated it twice so that it could do static linking. Good old days. You can tell with the gray hairs. I know all the old stuff. So a big innovation in CMake was adding transitive linking to CMake. So what this meant was that we've decoupled the indirect dependencies from one another. So only the direct users of a library need to adjust things if there's breaking changes. So this is a huge innovation. But, what about all the flags that go with it? Just doing the libraries was the first thing that was done, and it was something hard to do. We had to add graph analysis into CMake and basically improve the code. But after many years of seeing this problem, eventually modern CMake was created. Another generative AI image. I said, generate an image that shows modern CMake. I have no idea what this means, but I thought it looked really cool. Or maybe kind of scary. I don't know. Modern CMake's like a nasty kill robot or something? I don't know. All right, so the target and its usage requirements are basically at the heart of modern CMake. So in this right out of the CMake tutorial, I'm creating a library called math functions, and I give it a source file. And then I have some compile definitions. The first one is a private one, which means it'll only be used when I'm compiling myself. And then another one that is a public definition, which means anyone that consumes me is going to get that flag. And then I'm going to create another library here, the square root library. And I'm going to link that library to math functions publicly. And then the result, and then I'm going to create an executable called tutorial. And it has tutorial.cxx. And I'm going to link it to math functions. And then if you go down to the build, you can see the results of this communication from the developer of math functions to the user of math functions, this tutorial.cxx. When it goes to compile tutorial.cxx, lo and behold, there's a -d flag that showed up in my build compilation that got pulled out of the public compile definition. And then below that, when it actually goes to link it, you can see it links to math functions, which is what it asked for. And in addition, the square root library, because that was a transitive link dependency. Another important part of modern target-based CMake is that a library is treated the same if it's built within your project inside the same source, or if it's been pre-built by another generation of CMake and installed somewhere. So at the top, either the blue or the red could work. You wouldn't want to have both these lines in an actual code, but you can do add library bar, or I can do find package bar. But the rest of the code stays the same, and I just say target link libraries bar. So this is the ideal situation where I don't have to care where it's coming from, whether it's part of my build or someone built it externally. So that line of communication is there. I've gone through this before, and I thought I would throw it in here. The evolution of find-cute really sort of solidifies how this all happened and is a great example. So CMake originally had find-cute 3. And this is one of those find modules that worked like the other ones. It would locate cute, include paths and libraries, and set a bunch of variables. But if Qt version changed and needed something different, you had to get a new version of CMake or put your own find Qt 3 that was patched inside your project. Then came find Qt 4. And this one was definitely a step up. It basically, the only thing it did was find CMake and then use that to detect everything else. So what's happening here? The Qt developers found a way to communicate to CMake consumers through CMake. So CMake was able to do that, and then we were able to create imported targets. So CMake is actually communicating to the CMake from the Qt library maintainers. So now CMake doesn't have to change every time CMake Qt comes out with a new version. I can just reuse what CMake's doing. And find Qt5 obviously doesn't exist. And this is made possible because CMake created .cmake files. So in this previous version, CMake was creating the imported targets from the output of CMake. And then in Qt5, they used the CMake build system to actually generate .cmake files. So they figured out what goes into a .cmake file, and they shipped that with Qt. And now it's possible because CMake's finding. So again, the Qt developers are communicating to CMake via .cmake files. Then eventually you get to Qt6, which doesn't exist. And this doesn't exist because Qt6 actually builds with CMake and exports its own targets using CMake's target model. And Qt had to undergo a major build system conversion for this to happen. So this just tells CMake to look for Qt6 in the core module. And we've got the required thing there because CMake will error out if it doesn't find it. But again, this is a way of putting that pathway of communication. So some common target properties. You can set compile definitions, -d flags, compiler options, compiler features, which C++ standard you're using, or you can get even more finer granularity, precompiled headers, the include directories, the sources, link options, link directories, link libraries. There's a whole bunch of properties here on the targets. And the usage requirements you can create interface libraries. So interface means that it's for the consumer and not for yourself. So in this example here, you can see when we're building trunk.so, it actually doesn't link to root because that's only in its interface specification. But Leaf publicly links trunk, so then you can see that libroot shows up as well as libtrunk because it's set up as an interface library. So I'm communicating even more information when I set up my tool. It's not just how do you link to me, it's how, hey, when you link to me, you're going to need to link to me plus this other thing, but I don't need to link to that because I'm handling it some other way. You can take this a step further and have interface libraries. Interface targets doesn't directly create any build output. It may just be a set of properties that I want to communicate, like compile features. I create an interface and I want to just do compile features. So then anything that links to root, even though it doesn't actually provide a library itself, it can provide a handful of options for the compiler. And then, of course, CMake has a way of exporting these into these .cmake files. So this works by taking a config.cmake.in and replacing variables and eventually producing a config.cmake file. And inside one of those, you'd see it creating a library like a root interface imported. And then I'm setting the compile definitions, compile features, some interface compile options. They can be based on different build types. I'm setting the include directories, and basically, CMake can create these whole ability to do this and generate this for you. All right, so this even gets more fun when you talk about C++ 20 modules and the BMI. Nope, wrong BMI. All right, this is the built module interface. And this is basically it's kind of like a precompiled header. but it's a lot more sensitive than regular binary files. Can the BMI be reused between two things? It's kind of a compiler-specific question. It depends on the flags being used. So like C++23 and C++20 standards wouldn't produce a compatible BMI. You could still use the library and use a module to interface to it, but you would have to rebuild that BMI for each of them. Some things like verbosity and no verbosity, yeah, for sure you could do that. But it definitely gets complicated. There's a whole paper on this, if you want to read, Daniel Russo, on specifying interoperability of built module interface files. But I think the key point as relates to this talk is that for this to work, and for C++20 modules to work, you're going to have to specify this stuff in the build system and explain it to the build tool and have a way for that to be shipped around and communicated for consumers and for building it, because it gets a whole lot more complicated than just textual inclusion with header files. So in this example here, I'm going to create a library that has modules. And then I'm going to create a library, and this isn't complete valid code, but we'll call it pseudo CMake code. I'm going to create a library that does use C++20, and then I'm going to link that to as modules. And I'm going to have one that does use C++23, and that's going to link to has modules as well. And then I'm also going to create another one that says also use 20, but I'm going to have a private include flag that's include foo. So can I share the BMI between use 20 and also use 20? Yes, because they're going to have the same interface. Even though I've got different include flags, that's probably OK because it's a private include flag. And modules themselves, so this is the C++20 module example that Brett and I put together in a talk, and I updated it, new got built, but basically it's, when CMake went out of experimental. And you can see that to do modules, we're using target sources and creating a file set of C++ module types. And this allows CMake to generate the BMIs and to do the dependency trees. And you can see other talks or look at import CMake, the Experiments Over blog on the Kitware site, if you want to read more about how these work. But the important thing here is, this target model is sort of key for being able to do modules in CMake. Now, import std, everyone wants that, right? That should be simple. So it looks simple in the C++ code. So I've got a hello world, and I do import std in there, and then a main that calls my hello world function. And what does this look like in CMake 3.29? Well, up at the top, I tell CMake that we explicitly want import std for all the targets. So C++ CMake CXX module std set to 1. What this does is, across all the targets in this build, it's going to turn on the CXX module std flag. And then I'm going to create a library, uses std. And then I'm going to add some sources to it. And then I'm going to tell it that the compile features for uses std private, meaning that when you're building this one, I want to do C++23, which is what has support for import std. But my interface, I'm going to allow C++ standard 20. So I'm going to then create an executable main, and it's going to link to uses std privately. So internally, what happens is So I've got my library uses std, which has a private building C++ standard 23, the interface C++ standard 20, the CXX module is set to 1. My executable has C++ standard 20. It also has CXX module standard 1, but it's ignored because it's only valid if I'm using C++ standard 23. And then CMake creates an internal target that's the CMake standard std library. And right now, and that's why it's in experimental mode right now. Right now, CMake creates that. It actually compiles some code and then builds the BMI. There's a little bit of an argument who should compile that code. Should it come from the vendor, or should CMake have to compile it? And you run into trouble with, does the vendor then have to provide the debug, the release, and all these many different variants of the library. All right, so CMake, I think, does a good job at this and it's growing more, but let's take a look at some other build tools and their usage requirements. So CMake, there's a Git issue they had. They wanted to support private, public, and interface to improve dependency inheritance just like CMake. So they ended up with something very similar to what CMake has, and they're basically using the same target model that CMake has. Boost build has something similar. So if you create a rule, it's got requirements and usage requirements. And if you look at it, requirements is the list of properties that must always be present when the main target is built. So basically the private requirement. And usage requirements is a list of properties that would propagated to all the main targets that use this one and to all its dependencies, essentially the public requirement. Meson build has a declare dependency. It's kind of like this. I tried to dig into it, and I may be getting some of this wrong, so I'm not a big user of these build systems. I'm obviously a CMake guy. But they created this declare dependency, which is a lot like, and they said it was useful for doing subdirectories, subprojects. So it kind of models what CMake does. It's a little bit close, but not quite the same. Bazel seems to support this idea, except it only seems to work with include files. So in this example from there, they're showing foo depends on bar, and basically the allowed direct conclusions in the example listed below. For example, foo.cxx is allowed to directly include foo.h and bar.h, but not baz.h, because it's an internal header. So they kind of do it for includes, but not all the rest of the flags, as far as I can tell. I might be totally wrong. If anybody in the audience can correct me. Nobody knows. Okay.
What do you mean by includes only? Aren't these depending on other targets?
Right, but it's pulling along the include flags.
Oh, I see. You're saying that it only pulls the include flags.
Yeah.
The others.
Bill's saying he doesn't see how to express a private dep or a private compile definition or something like that. It might be possible, but he doesn't.
Yeah, it seemed more like a global thing. You just sort of set the flags. There wasn't ways to set flags on a particular target and have that pulled along,
No,
other than for...
You cannot, when you set flag in Bazel, it's always on the target itself. It's not transitive to the upper one. It's going to work for include, it's going to work for the linking, but it does not work for the flag on purpose. Google does not want to support.
Hey, there you have it. Okay, so includes and libraries are intentionally the only things supported in Bazel.
They do have targets, they just don't have all the same.
Yeah.
Yeah.
It's not quite as rich a target.
I think that's accurate. I use Buck at Facebook, which is kind of looks similar, and yeah, we also have same limitations. Like you can put compiler flags onto a target, which applies only to that target, and there's no way to make it apply to transitive dependency or the things that depend on it. Yeah, as far as I know, deps is private private dependency, and then you could use exported underscore deps to make the stuff that would depend on you also be visible. But as far as compiler flags go, yeah, I think your observations are accurate.
But to some extent, it does have this sort of target-centric model.
Yeah.
There's a directed graph,
Yeah.
So the answer is use CMake. As Bryce said, resistance is futile. We've got a standard build system. It's CMake. Another AI-generated image. But, you know, not everything's built with CMake. There's other build tools out there. And CMake's not the only tool that wants to use your libraries. And .cmake files are hard to read and write if you're not CMake. So the next logical conclusion in this evolution is CPS, the Common Package Specification. This was started by 2016, Matthew Wolke, works at Kitware, wrote a paper about it. There's a 2018, there was a WG21 paper. In 2022, there was a talk right here, down in the other room, I think. It was Brett and Daniel from Bloomberg did a talk about the need for something like CPS. In 2022 at CppCon, there was a group of interested folks got together, I guess a hallway track, Conan, VC Package, and others talking about this. This past year at CppCon, there were actually 3 talks about this, and in 2024, we are hard at work getting CMake to export CPS files. So CMake and CPS. CMake's package files are created by CMake and commonly installed alongside libraries on Mac, Linux, and Windows. So we've got a big market share. CMake can be used to create CPS files. And CMake projects, if we're lucky, there'll probably be some work, but if we're lucky, we're able to transition from CPS for free with an upgrade of CMake. There'll probably be some slight changes people are going to have to do, but the idea is we can move the ecosystem towards this richer model and having a way of declaring these libraries and providing that path of communication. So CPS provides a communication path from library maintainers to consumers. And who are the consumers? Some common consumers are, package maintainers, build systems, IDEs. And I really think this, in thinking about this, although I just was in here earlier and apparently some of these object-oriented principles are thought of poorly at BoostCon. CppNow. But the open-close principle, I always thought this was a kind of neat concept. The idea that you want software to be both open and closed, meaning that closed, I want to define an interface so someone can use it and depend on that being there in the future. And open, meaning, hey, I want to add new features as well in the future. And getting around this concept. So I would argue that the target model is both open and closed. The interface needs to be closed because consumers can then just use the library. They say target link library, but the interface needs to be open because the maintainer needs to add new features to the library. So I sort of contrived a little example here. So let's say in 2024 and 2025, I can say, target link library, my program to some fun library. In 2024, the fun library says I've got a public library that I link to called Hidden Fun. 2025, they're like, that Hidden Fun thing, I don't really use that anymore. It's no good. I'm switching to library More Fun. But up at the top, that code doesn't need to change because the the creator of fun library is able to communicate through exporting packages and through the target model that it's new, has this new dependency on a new library. So the target model essentially, during build, you've got include directories, libraries linked, compiler flags, and then consuming, you're going to have include directories, linked libraries, compiler flags. And you can consume it during the build or during a consumer's build. And how does this impact sort of the main problems that C++ community is having? I would argue that managing dependencies is definitely something this can help with. If we get to the point where CPS and build systems, so imagine a world, the build systems have this target model, all of them do, and then they can also create CPS files to communicate across the ecosystem. And then package managers don't have to repeat doing all the work. It could affect build times with modules. So if I've got all this information there, and then I can figure out whether the BMIs need to be recompiled. Understanding the target model is obviously important with dealing with CMake. I think getting this concept of modern CMake and targets is really important for developers. And then, of course, setting up toolchains and IDEs would potentially be made easier by having this model be more prevalent. So, summary, the status quo of passing flags around really isn't sufficient for building modern C++ with modules and huge dependency trees. Reuse requires communication from the package maintainers to the package consumers. C++ modules require more fine-grained information. And a build system with a target model plus CPS should be able to get us closer to the ecosystem we need. And another screenshot from the keynote this morning, basically build system to package manager interoperability, and that's, again, what this would help with. So I'd like to go back in time, give some thanks to Alexander Nurendorf, who championed CMake adopting to KDE, which was kind of a tipping point for CMake, and launched it into becoming the standard that's kind of become today. And why that's important in this talk is in 2012, modern CMake was created by Stephen Kelly, who was a KDE Qt developer. And then usage requirements and what I just presented today was created. So if KDE had adopted CMake, who knows if we would have stumbled upon this. But it's good to thank people. And even more thanks, Ben Bazel, coming up with the flag soup paper, Brad King, who's tireless maintenance of CMake and making sure that everything makes sense and is very consistent. Craig Scott for his contributions to the project, Matthew Wolke for his work with CPS, and the whole CMake open source community, and CppNow, where a lot of these conversations have happened, and of course Bloomberg Engineering, who's helping to drive some of these innovations. And thank you for coming to the talk, because I know you had other talks you could go to as well. And I'd like to open up to questions and hopefully some good conversation. I've left you plenty of time for that. So,
Yep. One question I have is, CPS is an excellent thing because it's gonna allow us to go away from the madness you have right now in package manager, where every package manager has its own compiler wrapper for the modern one, like Spack or Nix or Wix, in order to be able to inject correctly the flag, because most of the build systems don't do the stuff that you expect to it when you're a package maintainer. One thing, however, is the support is not there in every build system, right? Outside of CMake that just did it, like every other build system don't support CPS, right?
well, CMake doesn't even support it today.
My point with that was, I think it would be a great at least for for a long term, we are still gonna get like people that do C++ and still do makefile manually or run auto tools and this kind of stuff. If the CPS has something similar to pkg-config, where like you will take your CPS file generated by CMake and you get your raw flag directly in Make for like the people that log their Make manually, which there is a lot in the HPC world, that will help a lot, honestly. Just
Yeah.
It's a great idea. We have a project starting that's doing that. We can use more contributors, but yeah. So yeah, the goal would be to alias something called CPS-config to be package config, and then any build system supports package config.
I think you just got a contributor.
What?
I think you just got a contributor.
Okay, well, we'll find you later, and I'll help you find the URL and stuff.
Yeah, and I think we do want to take advantage of pkg-config and its files and looking at ways of potentially importing PC files and converting them automatically.
Yeah, some interop for PC files exactly would also be great. So that you wouldn't, if you missed a few CPS files, you could find a PC file and guess. Yeah, you could probably parse out the interesting parts. They're usually not that interesting. Usually it's just where's the include directory and where's the library directory for the most part, right? So that's the goal. But yeah, and it's also a nice greenfield C++ project. I know some people just want to contribute to C++ open source, and they don't know where to start, and all the interesting projects are enormous, like LLVM, and how do you get into that? So, contributors of all experience levels will probably find things they can help out with.
Related to that, are you aware of any active effort to integrate CPS to Bazel and also Meson, which are the two main ones?
Meson, yeah. One of the most prolific contributor to CPS-config is a Meson core dev.
Okay. Yeah. So Meson yes, but Bazel no. Okay.
We're ready to collaborate. So someone could be identified. Yeah.
Yeah. The
I would
question.
imagine you could write Skylark rules that could do this without patching Bazel itself, but I'm not an expert.
Yeah, and I think that was the idea of having some common format, and going.
Like Bill mentioned, it'd be nice if you didn't have to have a specific packaging logic for every single package in a packaging system. The same goes for interoperability with mono-repo build systems. It'd be great if you just said, oh, it's a CMake, you call CMake and then look for the CPS file, and that's all you need to know. It's a nice analogy for what we were talking about with C-line interop with CMake, where they have these file API. You can just say, hey, CMake, I want to know what you're doing, and it gives you a JSON file. It's the same idea, but for a packaging system.
Yes.
I have a question about those compiler flags, because I always think that compiler flags are the wrong things to specify on when I'm writing software. I need that compiler flag, but I don't want to say I don't want to have to say to compile my program you have to have a -f whatever. I would rather have a way to say I want my program needs to do whatever, instead of having to say I want to use that flag.
Yeah.
And I know that in CMake there's already the concept of I think it's a compiler feature, but there's no list of compiler features anywhere I can find.
It should be all in the CMake documentation, but yeah,
it's not easily found.
But that is a valid thing,
But
right?
it's
You don't want to have your CMake files that have very specific compiler flags in there. You want to have those abstracted in the CMake, in the language of the system,
What do I need?
Like I want include directories. I don't say I want -i flags. I want include directories, or I want this level of optimization, or I want to turn debugging on and off. So basically abstracting those features.
And sometimes the requirements for compiler flags are different between different tool sets. If you're using Clang, you might need to to have a compiler flag for something that you don't need on GCC or Microsoft compiler. I don't know.
Right, and then sometimes we abstract those commonly used things out into CMake and essentially teach CMake how to give you those flags compiler agnostically.
Yeah, but how does that translate into this this generic CPS or?
Mm-hmm. Yep.
How does those generic compiler features that CMake might understand, but Bazel might not understand, or some other?
We can describe, and we already do in the spec if you want to take a look at it, the same kinds of high level concepts. Like there is an include directories field. You could shove it into a compile options flag field, but you wouldn't. You'd want to use the right semantic field for that. And like Bill's like you were saying, there's some limits. Like, is this S-F flag have a thing that works across all systems? You know,
Yeah.
like what does that mean? But
the
like,
one thing
but it is a place where we could start adding more places, more of these things, in a way that would be portable across all the build systems. Whether every build system respected all the fields, well, you'd have to work with your maintainers at issues saying, hey, there's a new field for stack protection. Can we make sure stack protection gets a first class treatment if that's important to you?
Yeah, and some C++ features require that. Like if I want to use coroutines, I frequently have to add -f coroutines or not.
Yep. And that might be a usage
But it's
requirement of your
not
library.
clear to me as a programmer that specific feature needs that until I get never
So
trying to compile.
right. So the two things we can do right now are, one, talk to our tool maintainers about how important it is to us. A lot of times there are people on those in those organizations that want to help, and they could use the evidence to convince their bosses that it's a good use of their time. Two, and this applies to a lot of the open source tools, some of us just need to roll up our sleeves and start getting to work a little bit. A lot of these tools are maintained by volunteers largely, and there's no expectation that they have to do anything for us in particular. They have lives and jobs and things. So if we're wondering why coroutines aren't better supported in specific ways, it's probably because nobody did it, and it's not that much more complicated than that. If we can invent new ways to organize our community such that we can do a Kickstarter to get coroutines implemented, let me know. But short of that, like those are the two things that seem to be the things we can do like now. Almost all the open source tools, all the vendors have some sort of enhancement request system where you can chime in and say, yeah, this is important to me too. And the product owners, if you're loud enough, they'll have to listen on some level.
Any other questions?
Also point out the one thing you didn't get into too much, which is fine, but I'll point it out since we have time, is that packaging for modules is entirely an unsolved problem right now. Like we don't know how to build a library in a package, install it on a system that has modular interfaces, and then allow someone else to consume those, partly because of what Bill was trying to point out with, like there's an implicit imported target there, and you need to say, how do you parse that interface on its terms? It might have private include directories that you shouldn't see because you don't use those headers, only that module does. And there's no way to express that right now in our ecosystem short of, CMake import, export workflows. So the best option, that's what Bill's getting at one of his slides, is, okay, let's all just use CMake now. And that doesn't seem all that realistic. So that's another reason that CPS is interesting, is we don't have fields in there for modules yet, but it's something we could add reasonably and say, okay, well, this also has modular interfaces and it has private, compile definitions or whatever that is.
But in theory, if you bundling the whole source of the modules, it would be available there if you are able to link it correctly, or.
Well,
I didn't understand a little bit what do you mean packaging the modules?
So if you just
Is
create
that
a
just
library,
a binary?
yeah, binary
distribution?
packaging.
Like, it's not enough to ship the sources, you have to ship enough of a build system with the sources that you can compile that module on its terms. And so that would be what the CMake find
Yeah,
find package workflow
because-
is. It's enough of a build system that you catch up, but that's not portable. And IDEs aren't gonna get that information. So even the IDE, like autocomplete, where did this come from, is gonna be like limited by like those kinds of problems. Like it may not know there was that, you might get a red squiggly line, I don't know what this header is. Well, it's because you didn't see the private include directory, and like, well, how would it know? There's no standard for shipping that. So like, again, CPS could, like again, if people are enthusiastic about C++ modules, again, that's a mechanism we could use to get these things like shipped. So, and working in auto tools, if we can get the CPS config thing working and that kind of stuff. I mean, maybe never in auto tools, but it's a better shot there. But,
Definitely more likely to get CPS and auto tools than get them to generate .cmake files.
that's why I'm glad that Bill gave this talk, because like, to me, it also like in kind of a negative space way kind of explains why you need to get a better, more modern build system as just part of being in a C++ ecosystem these days. Like, there's a lot of limitations using hand-rolled makefiles and old autoconf and things like that are just, it's just over, like you can get away with it, but it's not great, and it's going to hurt your ability to get your jobs done and help your users the way you want to and stuff.
Yeah, I think that's just going to continue to be a bigger and bigger problem. The more rich feature set gets added into C++, the more demands on the compiler, and especially with modules. Because you're not going to do, C++, some foo.cxx, and if that's got some import module stuff going on, it's just not going to work. You're going to have to use a real build system. And whether or not it's CMake, it doesn't matter, but it's going to have to be a build system that knows how to do a lot of more stuff for you.
And it's a standard we could add things to. You could put provenance information in there and signing information in there and license information in there, like for those workflows that are really important. And right now, I don't know if everyone knows this, but there are vendor tools, and they try to parse your binary to guess where your code came from for like security reports, and that's silly. Like, you should just have a file that's metadata to describe the binary, like with hashes so you can collate or whatever, right? But like, it should be obvious. But like, we don't have that.
Yeah, another line of communication, right? Whoever built it, right, has got different versions of everything, and then that information needs to get out to the people looking to see, like, oh my God, there's a vulnerability in libpng.
Right.
Do I have it in my compiled version of
Whatever.
Or LZMA, right? Like, did you use that version of LZMA? I don't know.
Or XC?
Well, LZMA was the library.
Yeah.
And that whole thing, yeah.
I particularly like the...
Because sometimes the library is there, just compile it statically.
Yeah, I mean, yeah. Or three versions even. in different shared libraries. Yeah.
I particularly liked in the XC attack, the CMake attack.
The CMake part of the, yeah.
Did everybody see the CMake attack in the XC?
No, what was the CMake connection? XC attack.
Oh, one of the files that the person or persons entity created was a change in their CMake code that was looking for something that did sandboxing, and it was a check C source compiles, and the git diff, you look at it, and it adds this check C source compiles thing, and it's got like plus because they added a whole bunch of lines, and next to one of the pluses there's a dot right after the plus, so they added a random dot in there, which basically meant it wasn't going to compile anywhere. So even if you had the sandboxing, it was going to get disabled.
It disabled security features by adding completely invalid code to a try compile workflow. The try compile workflow was a proxy for, is the dependency version I need installed on the system when I build? And so because it couldn't query that in a more standard structured way, the best thing people tend to do is here's a sample piece of something that uses that interface. If it builds, I'm going to assume that's close enough. And so like, there's no way to say, is the sandbox module available? So they just built something. And the person with bad intentions took advantage of that by making sure it never built, so it never looked like the sandboxing was available, turning off a security check. I don't believe, I'm not a security expert, or I'm not super versed on this exploit. I don't believe this was part of the main exploit, but is another exploit in the same corpus.
Yeah, well, the exploit actually happened in the AutoTools version of it.
Yeah.
But it had a similar thing. But yeah, it does actually relate to this talk pretty well in that, if you had a way of defining what was on the system and ingesting those libraries, you wouldn't have to do checks like that. You would know what version it is, and then in the description file, you could check for things like that instead of.
The error could just say the library's not here instead of could not compile sample project. That's whatever, which is not the same.
Any other questions?
I might have one if you.
Sure.
Like, one thing you said, about the communication line is very nice. So what CPS provides is a communication line out, in fact. Whatever you compile, describe, and can be reused. What would be really nice to have in the long term is also a communication line in. Like when I build something with CMake, if you could have a standardized way across all build systems to just say, like, I want this set of target to just have stack protection from. I want this set of target to be C++20 and only that. I don't care about what the build system is doing and what the package author has put inside his CMake because he's God, he can do whatever he uses. I want to ensure that this package is building in C++20 and nothing else, that I don't have ABI problem or that I'm enforcing that there is stack protection of this set of software. On the long term, it will be very, very nice because once again, right now, if you take like the modern package manager, they literally wrap the compiler and inject their arbitrary flag inside the stuff just to guarantee this kind of stuff, which is amazingly ugly and breaks a lot of stuff left and right, including the IDE. If we could go away of that, that would be a major step.
Well, if you're okay paying with a broad brush, you can do that already with CMake, then you can validate it out on the back end.
Yeah, you can do it with a CMake through some flag, but you definitively cannot do it cross build system. One thing that would be nice is to go to one interface, standard one, cross build system.
I agree. There's it depends on how granular you want to be. But yeah, I agree. Like CMake has something called there's a few mechanisms. There's CXX flags, which is supported in quite a few build systems, which is just an environment variable saying, trust me, add these to the flags.
But even that, you can override it in your build system.
Right.
There are a lot of people that don't like CMake a lot. They override everything.
Which is partly why the combination of compile commands and the file API that we talked about earlier today are interesting, is because it does allow you some visibility into like what CMake actually does. So you could use that for validation. I'm not aware of a lot of public open source tools that do that, and it really should be fixed or enhanced or something. But the other big input mechanism would be actually the toolchain file mechanism, which was designed, if I'm not, Bill can correct me, for cross-compilation workflows for the most part, but it has a happy accident of having a kind of a nice structured way to define the environment, the base requirements of what you're trying to do. And BC package leverages that quite a bit and then some to get BC package to work. It's almost entirely implemented as a toolchain file, which is funny, but it works. So I think there's a standard there kind of missing. So if that's what you're getting at, I think I agree. I'm currently tackling the CPS thing. So maybe if this gets traction and momentum, I can move on to that is my next one or something. But if someone else wants to talk about it, that'd be interesting. I'm like a standard that's like toolchain file, but it's portable, and we could reasonably expect all the build systems to say, I gave you this toolchain environment spec, use it, and it includes stack protection and stuff.
I think that kind of goes to your question about the flags, right? And teaching CMake some more abstract name of the flag. And we do that. I believe we added something for turning warning levels on and off.
Well, at least BC package and Kona both know about toolchain files. I know how to inject.
Right, but this is outside of toolchain files.
Yeah, this is outside of toolchain files. So in those build systems, you would give a higher level, like I need to do debug, and then it would like know that, oh, that means the build type is this, or you could say like, I want platform independent code to be generated, so it knows, okay, that means you need the fpic in the toolchain file. So it's at a higher level at the packaging system. It doesn't communicate that way through CMake, because CMake doesn't have, well, actually it does, has the position independent code.
Yeah, that's what I'm saying.
It could do
CMake
that.
can be taught
Yeah.
to do common flags. And I
Right.
think we did do something with warning levels where you could set it.
We did for warnings and errors. Right.
Yes,
per
warning as
target-
error,
yeah,
yes.
So per target, you can set you want warnings to be treated as errors. And then at the higher level, to your point, you can say, never mind all that, I'm just building right now. Like dash, no warnings as errors. 'cause-
WRO is a typical thing.
Right.
When you're packaging, like you have countless number of packages by default. Put WRO
Yeah.
when you compile it, even in realism, and it's gonna break in any package
Right.
manager because you're
Every
gonna
time you
change
upgrade
the
the
compiler.
compiler. Every time you upgrade the
And
compiler.
this is a typical thing that the package manager wastes days of fixing that all the time. Because every time you have a new release, you have generally a patch file, which is like
Right.
reapplying a patch on the CMake or whatever you have on there. Which, like, if you can rid all of that, if you in the long term you could get rid of all of that, that would be like a major improvement.
But that is something that is in CMake now. We added a feature for
So
that.
yeah, if you ever see -w error as such in a CMake file, well, first of all, they need to upgrade to CMake 3.27 or something, which isn't that new, but it's old. It's new enough that like stable Debian doesn't have it yet and things like that. But
Which should be standard in around 10 years. It's okay.
yeah, like the CMake release cycle is still like 3 years to get the feature on most of the OSs. I don't know why it takes that long, but it is. CMake's actually pretty stable. They could upgrade it a little more aggressively than they do, but anyway.
All right, I think, any more questions? Okay, we'll end it here then.